Greetings, Algebra 2 students. This is the notes for 1-7. We're going to talk about two things here, both talking about inequalities. So when you're talking about inequalities, again, you're talking about a range of numbers, not necessarily just one single solution. You're talking about an area or a group of numbers that are all going to be solutions to the problem. So we're talking about inequalities and then linear inequalities. Let's get right into it. So if compound inequalities means you're going to be going either in two directions or one direction, okay? So you're going to use and or. So what that means is something like this. Both inequalities have to be true, okay? So if I let this be like 0, -1, -2, 1, 2, 3, greater than or equal to -1 would go this way. Less than -2 would go this way. So my only solution would be between those two. Those would be my only solutions, okay? If I say or, that means it could go either way, okay? As long as it satisfies one, it satisfies the whole problem, okay? So if I say 0, 1, 2, 3, 4, 5. If I say less than or equal to 1 or greater than or equal or greater than 4, as long as it satisfies one of these conditions, it's still a solution to the problem, okay? And this happens quite a bit. You're either going in opposite directions or going in the same direction or towards each other here, okay? So if I look, this would be a compound solution. So 2x plus 7 has to be between 13 and 17. So now it's kind of like I do two little algebra problems within one. Okay, so I subtract 7 kind of from everything. So that's going to be 2x less than or equal to 10. 13 minus 7 is going to be 6. So divide everything by 2. So x has got to be less than or equal to 5, but 3 is less than x. So when I look at my number line, so 3 is an open circle less than x. 5 is a closed circle because of that equal sign, because of less than or equal to. So between 5 and 3, that's going to be my only area of solutions. So similarly here, if I add 4 to both sides, so that's going to be 12 less than 3x less than 15. So divide by 3. 4 less than x less than 5. So that is my only area that's going to work, is between 4 and 5. So now these are a couple of or solutions, so I could be either or. So I got two little mini inequalities to work with. So -10x minus 3 is going to be less than or equal to -40. Divide by -10 means I have to switch the direction of my sign. So there it becomes 4. Add 10 to both sides over here. 3x less than or equal to -15. Because I'm not dividing by a negative number, my sign stays the same. Even though there's a negative number involved, my sign stays the same because I did not divide. Over here, I divided by a negative number. So 1, 2, 3, 4, 5, -1, -2, -3, -4, -5. So if I go less than or equal to -5, I'm going that way. Greater than or equal to 4, I'm going that way. All right, so that's going to go apart, and that's going to be kind of my solution area, either this way or this way from those boundaries. So now number 8, same kind of idea, this or this. So I subtract 6x, add 5, So that's going to be 2x greater than 4. So x has got to be greater than 2. Subtract 3x, subtract 3x, subtract 4, subtract 4. So x has got to be less than or equal to negative 7. So x has got to be less than or equal to negative 7. So at negative 7, I go smaller. Greater than 2, I go bigger than 2. That's what my graph is going to look like, okay? Now, when I go to an inequality with two variables, it's going to be slope-intercept form, but instead of y equals mx plus b, it could be y equals less than, y equals greater than, y equals less than or equal to, y equals greater than or equal to something, okay? But it's still going to have this form. It still could be like 3x minus 4, or 2x plus 6, something like that. All right, 4 less than or greater than, I use a dotted line. For these two, for the less than or equal to, greater than or equal to, I use a solid line. Okay? So I shade, I kind of indicate where that area is. Remember, we're not just talking about one line as a solution. Now I'm talking about a whole part of the graph. So I might have a dotted line and say everything down here is part of the solution. The shortcut, usually if it's greater than or equal to, less than or equal to, be real careful here. This is a place where a lot of kids get this screwed up. And it's always a good idea to test a point. Test a point and see if it's true or false. Easiest point to test is the origin, 0, 0, if you can do it. Otherwise, pick something simple. Usually 1, 1 would be pretty easy, or something simple that you can test. So when I go to look and graph, first thing I want to do is convert it to slope-intercept form. So that'll be 3y less than or equal to negative 2x plus 6. So y less than or equal to negative 2/3 x plus 2. So plus 2, I'm going to go down 2 over 3, down 2 over 3. This tells me it is a solid line. Now I have to figure out which way to shade, okay? I'm going to test 0, 0. That's going to be my test point, okay? I'm going to test 0, 0. And I'm going to test it back in the original equation. So 2 times 0 plus 3 times 0 less than or equal to 6. Is that true? Is 0 less than or equal to 6? That's true. I'm going to shade towards that. Okay, I'm just going to draw arrows and say, hey, everything underneath that line is good. So that's all I do. That's kind of the gist of what I'm trying to do. So for this one, if I'm going to add x to both sides, so 2y greater than x plus 4, divide by 2. Y greater than 1/2 x plus 2. So I'm going to start at 2, up 1 over 2. And this is a dotted line because it's just greater than. Okay, so it's a dotted line. Again, I'm going to test 0, 0 because 0, 0 is the easiest thing to test. So negative 0 plus 2 times 0, is that greater than 4? Is 0 greater than 4? That is false. Shade away. Now we get a little bit trickier. We still got to remember our rules. So for this one, negative y less than or equal to negative x minus 2. So I have to divide by a negative. So y is going to be greater than x plus 2. Greater than or equal to. So on the graph, start at 2, slope is 1. Test 0, 0. Is 0 plus 0 less than or equal to -2? No, that's false. So I'm going to shade away. So start off with -2, up 2 over 3, up 2 over 3, dotted line. Test 0, 0. Is 0 less than 2/3 of 0 minus 2? True. Is 0 less than -2? False. I'm going to shade away. And if you just want to draw arrows to indicate which way you're shading, I'm perfectly okay with that. So, main is $15 spent at the fair. It costs $5 for admission, 75 cents for each ride, 25 cents for each game. Write an inequality for the number of ride and ticket games he can buy. All right, so first things first, it costs $5 just to get in. So that means he's down to $10 left. Okay, so $10 left, and that's going to be, his ride tickets and his game tickets. So it's going to be 75 cents for each ride plus 25 cents for each game. And all that's going to be less than or equal to 10. So 0.75 for each ride, 25 cents for each game. And all of that is less than or equal to 10. So if he buys 10 game tickets, how many ride tickets can he have? Well, that's just going to be 2.5. So he's going to left 0.75 R less than or equal to 7.5, not 10. Sorry, my mistake. So he can buy up to 10 ride tickets. So what's the maximum number of ride tickets he can buy? So if he buys all rides, no games, so basically 0.75 R less than or equal to 10. So I'm going to divide that. So his ride's going to be less than or equal to 13.3. So we can only really buy 13 ride tickets. Then the game tickets, it's kind of like no rides, all games. Should be up to 40 tickets. So he can buy up to 40 game tickets. Okay, I look forward to answering your questions.